Greetings, math analysis and trig students. This message is brought to you by SEPTA. One public service announcement I would have with regard to SEPTA is, say you take the train in from Wynwood to the city. Often it's kind of expensive to buy a ticket on the train. So if you do buy a ticket on the train, I believe it's $5 or $6, make sure you bring that ticket stub to the ticket office as soon as you arrive in Philadelphia. The ticket office, they will give you a return trip for about half the price of your trip into the city if you show that stub. If you don't do that, you'll have to pay the same price on the train in both directions. So trying to save you guys a few bucks. All right, regardless, quick video on rational functions, okay? So we talked about these a little bit in class, generally about what an asymptote is, how the graph looks of the parent function, y equals 1 over x. I wanted to make a video just so you have this down on paper or on the screen, because there's a lot to remember. All these details are important, okay? With respect to the discontinuities that could happen in the graph, right? Values are usually excluded from the domain if you have a rational function. Right? There are some x values excluded. Values for x that make the denominator 0 are excluded from the domain. So one thing you've got to make sure you understand is how to find first the domain of a rational function. So just set the denominator equal to 0 and solve it. Find those x values that make the bottom 0, and those are excluded from your domain, okay? Now, after you find those values that are not in your domain, what those values produce is some kind of a discontinuity, okay? And there are two types of discontinuities you might have, a vertical asymptote or a hole. We talked about both of those in class also. All right, so if you cancel out a factor, so let's even do a little example. All right. What about we look at problem, the middle one. So say we do problem y equals x minus 2 over 3x cubed minus 7x squared plus 4. Now this is kind of a hard one to do, but based on the last unit, this is a cubic polynomial that I've already taken the liberty of factoring, meaning I found on the calculator, I found a root was x equals 1, so one factor will be x minus 1, and what you're left with is, I've already done this, a quadratic that factors into 3x plus 2 times x minus 2. So we have a problem where the denominator factors like this. So I can even erase this and just replace it with this problem. Say this was the original problem. I've just factored it for you. Okay? Always a good idea to factor the denominator to start anyway. The first question I ask you for this kind of problem is, what is the domain? Well, the domain is all real numbers except for the values for x that make the bottom 0. Now that it's factored, you can see positive 1, negative 2/3, and positive 2 are excluded from the domain. Okay? Now, like I was saying, at each of those three numbers, we're going to have either an asymptote or a hole. All right? Now, you see that x minus 2 is also a factor of the top, so we can cancel out the factors of x minus 2 in simplifying this. All right? Because we factored out because we canceled out the factor of x minus 2, this guy, positive 2, is going to produce a hole. These guys did not cancel out. They're going to be the vertical asymptotes. Okay? So what we're going to have is often on a test problem, I ask you for the domain, and then I also ask you for the vertical asymptotes. So that's going to happen. I reserve VA at x equals 1 and x equals negative 2/3. And those two x values will have vertical asymptotes, okay? And then you'll have a hole at the x value where this canceled out. So at the point where x is 2, we can plug in 2 now for x. We get 2 minus 1 is 1. 3 times 2 plus 2 is 8. So we have 1 times 8 is 8, 1 over 8. So 2 comma 1/8. I've just plugged in 2. I've plugged in the x value into the simplified function to find the y value of that hole. We couldn't plug in 2 to the original function. We would have divided by 0, which can't happen. Right? But remember, to start, you want to find, you're always going to be asked for the domain, which is all real numbers but the x values that make the bottom 0. At those values, you're either going to have an asymptote if the factor is not canceled, a hole if the factor is. Okay? So I've done that. Now, we also have what are called horizontal asymptotes, which I didn't discuss so much in class. Okay? Now, the parent function, 1 over x, has a horizontal asymptote at the x-axis. Now, 1 over x is an example of a rational function where the degree is lower on top than it is in the bottom. right? Y equals 1 over x. The degree of the top is 0. It's a constant. The degree of the bottom is 1. It's linear. A constant over a linear function. The degree is higher on the bottom. Whenever that happens, whenever the degree is higher on the bottom, we're going to have a horizontal asymptote at the x-axis at y equals 0. So if we wanted to start to graph this example that I did on the board, the middle one here, let's graph it right here. The x-axis itself is going to be an asymptote, okay? We're also going to have two asymptotes, one at x equals 1. So let's say that's 1, that's negative 1 there. So x equals 1 is going to be an asymptote. And then x equals negative 2/3, right about here, will also be an asymptote, okay? It's kind of a weird graph, right? And then we'll have a hole at the point positive 2, 1/8. All right, so here's where x is 2, 1/8 is about there. We're going to have a hole there, okay? So one thing we know, remember, this is an asymptote. So just being able to sketch a quick graph, you can use your calculator to double check, but this is going to come in 3 parts because we have 2 breaks to the graph. One part's going to be up here. Look what the rational functions usually look like. All right, so that's going to be one part of the graph. Another part, if you wanted to find the y-intercept by plugging in 0, you could kind of get a better sense of where how the graph's going to look. But I know from past experience it's going to look like this, almost a parabolic-looking piece of the graph in the middle. And the third part of the graph is going to be up here. Okay, and this is how often the graphs look that have 2 vertical asymptotes. Okay, now you drawing these from scratch is kind of a pain, just to be honest. It's hard to have you do this in a test because you would have to really choose a bunch of points for x to get it very accurate in the 3 sections. All right, but using a calculator to check your work is very helpful, and just make sure you understand what an asymptote is. Right, it's a line that the graph approaches but never reaches. Okay, so that's consistent. The x-axis is our horizontal asymptote, y equals 0, and we have vertical asymptotes here and here. So I'll make a note of that here though too. Horizontal asymptote at y equals 0. And again, that's going to happen whenever the degree is smaller on the top. Here we have a linear polynomial divided by a cubic. The degree is smaller on top. We've got a horizontal asymptote at y equals 0. All right? So a tricky graph, but that's how this one would look. Now, I'm not going to go into graphing all of these. The video would get too long. But just so you know this, if the degree is the same top and bottom, this has nothing to do with vertical asymptotes. The degrees just tell us about the horizontal asymptotes. And we'll discuss this more in class. But if the degrees are the same, they're both cubics, what we do is, let's like a 1 in front, right? We divide the lead coefficients to find the horizontal asymptote, okay? So the horizontal asymptote for this one, vertical asymptotes and holes, we do the same way. That's totally based on the domain, and then if a factor cancels or not, okay? For the horizontal asymptotes, it's all about the degrees of the polynomials in the numerator and denominator. In this case, the degrees are the same, so we have a horizontal asymptote here at 1 over 3. Y equals 1/3. So there's going to be a horizontal asymptote a little above the x-axis at y equals 1/3. This graph is going to be significantly different than this one, okay? This is just for this guy. And last, if the degree is larger on top than it is in the bottom, with respect to horizontal asymptotes, there will be none. There will be no horizontal asymptote if the degree is higher on the top than it is in the bottom, okay? So just a little refresher on how to graph rational functions, and then also, hopefully from this video, you know how to find horizontal asymptotes, okay? And how they apply. We'll put all this together in class, how this applies to graphing in general, all right? But just a lot of detail to this unit, so I want to make sure I had this down on a video for those who might want some repetition, all right? Peace.